Welcome back. Hello, everyone. We welcome back you all to our presentation on electrostatics. In our previous presentation, we were calculating the electrostatic force between two charges using the Coulomb's law, and we did quite a number of examples on that. Now I'm going to take you a little bit further. Now we are going to look at calculating the net electrostatic force on a certain charge due to the influence of the other two charges. So, um, suppose we have got the following. Suppose we have got the following examples. Suppose we have got the following charges. Sorry, um, we have got charge one. Um, we have got charge one, which is plus 2 nanocoulomb. Then we have got charge 2, which is plus 1 nanocoulomb, and then we have got the last charge, which is charge 3, and it is minus 2 nanocoulomb. Then we are given the distance between charge 1 and charge 2, and this is 200 centimeters, and then charge 2 to charge 3, this is 150 centimeters, right? So that is the scenario that we are presented with. So we have got three charges here, and they are in a linear form in a straight line: charge 1, charge 2, and charge number 3. Then the question says, what is the net electrostatic force? What is the net electrostatic force? Right, what is the net electrostatic force on charge Q2, right? Due to the other two charges. Due to the other two charges. Right, like that. Now, how do we deal with this scenario? The only way of calculating the net electrostatic force is for us to make use of our previous formula from the Coulomb's law, right? We calculate the electrostatic force between Q1 and Q2, and we calculate the electrostatic force between Q2 and Q3, and we put the two together. Because remember, when we calculate net force, we are summing up the two, right? Now, as we do so, we must remember that these are charges, and they have got different influence or interference on each other. So what can assist us also is to come up with a free body diagram, right, which can show us the direction of each force. Now, our frame of reference or the charge that we are focusing on is charge 2, which is Q2. Because the question says, what is the net electrostatic force on Q2 due to the other charges? So in other words, we are saying Q1 is influencing Q2 to behave in a certain way, and Q3 is also influencing Q2 to behave in a certain way, right? So we need a free body diagram that is going to guide us to do our calculation. So I put a dot, and this dot is going to represent Q2, right? Now I look at the relationship between Q1 and Q2. They are both positive charges. They repel each other. In other words, Q1 is going to be pushed to the left because this is repulsion, and Q2 is going to be pushed to the right. You understand that? So our focus is not on Q1. We worry less about the behavior of Q1. We focus on what Q1 is doing to Q2. So Q2 is going to move to the right, and the Q1 is going to the left. So we take the direction for Q2, which is going to the right. So you indicate here on your free body diagram, and this is going to represent the electrostatic force between Q1 and Q2. Right. So when you calculate that force FQ1, Q2, you must know that the direction is to the right. Remember, these are forces and these are vector quantities where direction must be monitored, right? Then when I look at the relationship, what is Q3 doing to Q2? Q3 is negative and Q2 is positive, attraction. So Q3 will migrate to the left and Q2 will be pulled to the right. So in other words, again, my direction for this one is also going to be going to the right. So this is going to be FQ3, Q2. Right. Let me emphasize on the issue of direction because I know that's where most of our learners will have a challenge. We draw a free body diagram and the dot represents charge 2. Right. So we look at the relationship between charge 1 and charge 2. They are both positive repulsion. Charge 1 will go to the left. We worry less about it. Charge 2 will go to the right. So we are focused on Q2. So we draw a free body diagram, which is going to the right. Then between Q2 and Q3, Q3 is negative, that one is positive. Attraction, Q3 will go to the left and Q2 will go to the right. So we are worried about Q2 again. So our direction also for FQ3, Q2 is also going to the right. Now I need to divide my page a bit and have two columns. On one side, I am going to calculate FQ1, Q2 using the Coulomb's law, which is K Q1 Q2 over R squared. Then on the other side, I'm going to calculate FQ3 Q2, which is equals to the constant, then the constant, which is going to be the constant, and then Q3 Q2, everything over R squared. Perfect. Let me start with FQ1, Q2 there. Let's do the substitution together. FQ1, Q2 is equals to, our K is 9,0 times 10 to the power 9. You close. Our Q1 is 2 times 10 to the power negative 9. We have been dealing with nanocoulombs for a long time now. So that one is much easier. So charge number 2, it's 1 times 10 to the power minus 9. You close everything over. Our distance is supposed to be in meters, that is centimeters. So you divide by 100 there, you get 2 meters, and don't forget to square. Is that okay? So you take your calculator, FQ1, Q2 is equals to, this is newtons, and according to our free body diagram, direction is right. Perfect. So I need my calculator here. And on my calculator, I'm going to put the fraction and open the constant 9,0 times 10 to the power 9. Let me close here. I open 2 times 10 to the power negative 9, 2 times 10 to the power negative 9. I close, I open 1 times 10 to the power 1 times 10 to the power negative 9. I close and I close again. Then I've got my 2, I close squared. Then everything, I'm getting 4,5 times 10 to the power negative 9. Right. So this is the size of FQ1, Q2, right? So FQ3, Q2, I'm going to substitute as well. FQ3, Q2 is equals to, my K is 9,0 times 10 to the power 9. I close, my Q3 is 2 times 10 to the power negative 9. I close. Q2, it's 1 times 10 to the power negative 9. I close everything over My R squared there, it's 150 centimeters. You divide by 100 because we've got 200 centimeters in 1 meter. So you get 1,5. And don't forget to square. So your FQ3, Q2 is equals to, and these are newtons also, and direction is also right according to our free body diagram. Looks beautiful, right? So you need your calculator, friends. Let's get used to our calculator, Casio. We've got our fraction there. We open twice, and then we put our 9,0 times 10 to the power 9, which is our constant. You close. Then for charge 3, it's 2 times 10 to the power negative 9. You close. I forgot to open there. Let me go back a bit, and you can also correct that. Then I open 1 times 10 to the power negative 9. Right, you close there twice because you've opened twice. Then it's you open on the distance 1,5, you close, and that should be squared, and I'm getting 8 comma sorry, it's 8 times 10 to the power negative 9. This is newtons, and our direction is right. So the direction must come from the free body diagram. So you can determine your direction before you even start the calculation. So our net electrostatic force on Q2. So the formula says F net is equals to FQ1 Q2. It's positive because it's going to the right, plus FQ3 Q2. It's also positive because it's going to the right. Right. So F net is equals to, how do we calculate, which means we need to add those two. So FQ1 Q2, I got 4,5 times 10 to the power minus 9. I close, plus I'm getting 8 times 10 to the power minus 9. I close. Right. So my F net is equals to, I need my calculator again, friends. So I have got 4,5 times 10 to the power negative 9. I close, right? Plus, I open 8 times 10 to the power negative 9. 8 times 10 to the power negative 9. I close. Then I'm getting 1,25 times 10 to the power minus 8 newtons. Since I'm getting F net positive, it means my overall direction is right. Now let me take a few minutes to explain this calculation and also try to make some clear conclusions and analysis here. Now, friends, before I even start the calculation, by mere looking at the charges, remember we said there are two factors which influence electrostatic force: the magnitude of the charge and the distance. Now, given the fact that Q1 and Q2, they are almost similar in magnitude, it means the charge that is going to have a greater impact or a greater influence on Q2 is the one that is closest to Q2. So you look at the two distances. Q1 and Q2 is 200. Q3, Q2 is 150. So it means Q3 will have much more influence on Q2. So since they are unlike, it means the attractive force of Q3 overall, it must have a greater influence. Right? Even if Q1 was negative, still my F net is most likely to be right because Q3 is much closer because of shorter distance. Remember, the shorter the distance, the stronger the electrostatic force. So this is very correct. And also my free body diagram is also confirms that. So it means this is the net electrostatic force acting on Q2 due to Q1 and Q3. So overall, Q3 is going to be attracted or is going to be pushed towards the right. So this is the end of my calculation where we have got three charges. So just be careful. If you are supposed to calculate the net electrostatic force on Q1, it's the same story. But for your distance, you will have to combine the two distances so that you get the correct distance between Q1 and Q3. Now, in our next presentation, we are supposed to be looking at three charges again, but now it will be at an angle, and then we use our Pythagoras theorem, and we get the resultant force on those three charges that are at an angle. Thank you so much for joining H Blush. We greatly appreciate your support and your attendance as well. We meet again and let's brace up for better calculations. And we always use a calculator to verify our answers. Thank you. Take care. We love you all.